Hi, welcome back. Still on our topic, sets and operations of sets. Today's parts, we are going to deal with operations on sets, starting with intersections of sets. Now, there are three operations on sets. We have intersection with that symbol, we have union sets, and then we have complement of a set. These operations help us to construct sets from existing ones. So one may ask why the need for these operations, because out of these operations we can get a number of other operations. Things may seem abstract because we are not into the advanced aspect of math, but don't take any of these topics for granted if you really want to understand math and take it to another level or step boldly into the math space. Now, without further ado, let's start with intersections of sets. We will deal with the rest later in the subsequent episodes. I'm going to read things here because I can actually get everything here unless otherwise stated where I'll be writing. So now, we have the set of objects, right? The intersection of a set, that's the definition. The set of objects which belong to set A, right? Set A, and at the same time belongs to B is called the intersection of A and B. So simply put, or in grammar, intersection where two or more things meet at the same place or at the same time. Let's put this at the back of our minds. Now that is A with this symbol as if N intersection B, right? The symbol with that, this symbol means intersection. Therefore, P intersection Q means the intersection of the sets P and Q. For example, if A has a set of elements, meaning 2, 4, 6, 8, and B also has 1, 4, 8, then A intersection B, is equal to the elements 4 and 8, since 4 and 8 belong to both sets A and B. Because if you take A, 2, 4, 6, 8, and then going to look at B, 1, 4, 8, you can see that 4 appears here, is also here, 8 is here, and 8 is here. Besides these points, there are no other elements that reflect or appear in the two sets. So it's as simple as that. That's the simplest one. Now, we are saying that the shaded regions in figure 1.4, right? That's point I, and then B, and then 2, right? II represents A intersection B. It's as simple as that. We were introduced to a Venn diagram shortly, right? So this is the whole region, the union set, I should call it, that's the U. And then we have the subsequent or the other sets in that particular union set. So we have A, we have B. We can see that A and B has a common shaded region. So this shaded region is what is known as the intersection of the set. If you draw this and draw this, they are meeting at the same time, meeting at the same point. The same thing goes for this. That's another representation. So take note of these. In OBJs, you may be asked to do this, or maybe asked to find the answer among the options. It's as simple as that. Just look at it very carefully, right? So we'll deal with them later on, where we are going to do practical operations or examples. So that is, our main focus is on solving more examples. So here we have illustrative examples. We have example 1. We are saying that if P has element of 3, 6, 9, and Q has 1, 3, 5, 7, 9, then P intersection Q is equal to the element 3 and 9. Why? Because we see 3 here, we see 3 here, we see 9 here, we see 9 here. If you can check through, other elements are not appearing here and here, right? Besides 3 and 9. So it's as simple as that. The same thing is applicable to example 2, right? So we have Q has element of 4, 8, 12, 16. R has element 12, 13, 14, right? Then Q intersection R, we are having 12. 12 is here, 12 is here. Besides, or apart from these elements, none of them is appearing here and here at the same time. It's only 12 here. So you can see that the textbook has both the text or the numbers. It's as simple as that. Now, continuing to example 3, we are saying that find A intersection B. Here we have to do calculations. If A has elements such that X is greater than or equal to 2, and then B has elements such that X is less than 5, where X is an integer. Now, here, pay rapt attention. This is where some people may lose focus or may think this is difficult, and then they start to panic. Right. So when we are giving such example, I told you always make it a point to write things down. Don't assume, don't be trying to be a magician, conjuring things in your head. Put things down. Right. Now, we are saying that with the solution, if the sets are identified by an inequality, right? Inequality, these are the signs. Inequality, we were introduced to the previous episode. It is always advisable to list their members first. Therefore, listing the members of set A and B, we have what? A has element -2, -1, 0, 1, 2, 3, 4 up to 4, and then with the ellipses. Bear in mind, I told you with inequality, right? We have these signs and this sign. Whenever you see greater than or equal to, it means that extreme, that number is included most of the time. That's one of the tricks to note. And then another condition that we were giving is that number such that X is an integer. We were introduced to what integers are. Integers are whole numbers including 0. So always make sure 0 is included, with the rest as negative numbers and then positive numbers. That is why we were saying that if X is such that X is greater than or equal to 2, then 2 is included, right? So we are listing. So listing -2, -1, 0, 1, 2, 3, 4, because it's greater. So ellipses, we are listing until we are tired. Greater than 2. There were no other constraints, so that's why the ellipses are here. So you can list as many as you want until we are tired. It's as simple as that. Now, when you move to B, we have it also states that such that X is less than 5, and X is an integer, so it means that X0 will be included with what, considering the main constraint, which is what, less than 5. So if it's less than 5, so we can start from, we can still start from anywhere at all, but they started from -2, and I think obviously because the first condition started with 2, you can list anything, right? So -2, -1, then 0. What is important here is that the constraint was +5, less than +5. So that is it. So 0, -1, -2, -1, 0, 1, 2, 3, 4. We can't include 5 because it should be less than 5. That was the constraint or the condition. I can drag it once again for you to see that. You can see it here. Here, the constraint here. That is it. So moving back here, it's as simple as that. So, and whenever you are listing negative, be careful. Sometimes when you are saying a -2 is less than -1, you get confused. Now, when we are listing numbers, any number without a negative sign in front, then 1, 2, 3, we are increasing that sense. But the moment negative comes in front, it means that the greater number with a negative sign is rather the least number. So that's what you should take into consideration, or you should take note. It's as simple as that. So I know this may confuse a lot of us. Even when I was at your age or at your level in terms of math learning, the negative was confusing me. Which one is bigger? So a bigger number with a negative sign in front is rather the least number, the smaller number. So -4 and -5. Which one is greater? The greater number is rather this. -4 is bigger than -5. So that's what you have to take note. So we will see you in the next one dealing with disjoint sets. Now we have dealt with what? Intersection sets. So stay tuned, enter boldly into the math space, like and share, and let's hit Operation 1K members. See you soon. Bye for now.